Good afternoon, my name is Piero Sanchez,
And I am Akira Toma.
and we are both members of the blockchain team of Wolfram Research South America, and we're going to show you the new additions to the blockchain integration for Wolfram language. Like, for example, the new ARC blockchain. Yes? And
And I'm going to talk about the Oracle progress we've been doing.
Okay, so for those of you that are not familiar with the topic, let's start with the question, what is a blockchain? So there's really no standard definition for a blockchain. We usually have to adapt to the different architecture for each blockchain, but just as a general idea, a blockchain is a decentralized or distributed append-only ledger. Here in the image below, we can see that each of these nodes, each of these dots represents a node in the network, and each of these nodes has a copy of the blockchain. And the way they agree on the validity of this blockchain is by a consensus algorithm. Also, a common architecture for a blockchain involves making set of transactions, then putting those transactions inside of a block, and then linking each new block cryptographically in a sequence or a chain. Yeah. Okay, so how can we interact with a blockchain using Wolfram language? Here we have some functions, some reading functions and writing functions. Here, blockchain data is used to get some general information about a blockchain. Blockchain block data is used to get the information about a specific block in the blockchain, right? So each block is has a set of transactions inside, and we can look at the details of each transaction using blockchain transaction data. And finally, each transaction is usually the exchange of currency between sender and receiver addresses, and we can look at those addresses in more detail using blockchain address data. So if we want to add information to the block, if we want to add a transaction to the block, we have to use blockchain transaction to first to create a transaction object. Then we have to sign that object using blockchain transaction sign, and finally send it to the blockchain using blockchain transaction submit. So all of these functions work for the Bitcoin and Ethereum blockchain, and we are now adding support for the ARC blockchain as well. So let's talk a little bit about ARC. So ARC is a delegated proof-of-stake blockchain that offers tools for blockchain creation. This delegated proof-of-stake is the name of their consensus algorithm, but the way it works is that every address inside of the ARC blockchain can vote for a specific delegate, and they are called delegates, and by staking their balance, so the money they have, and only the top 51 delegates are the ones that are allowed to forge a new block. So that word, forging, is the equivalent to mining in Bitcoin. So they're the ones that have the job to pack these transactions inside of a block and then add this block to the blockchain. Yes, so here's the page for ARC. And now, thanks to the partnership between ARC and Wolfram, we're adding these reading and writing functions to connect to the ARC mainnet and DevNet networks. Okay, so let's start interacting with ARC by creating a simple transaction. In this example, I'm going to send some ARC from an existing address to a newly created address. So this could be like me getting my personal information and starting to send some ARCs to a friend of mine, for example. And we can do this in these 3 steps: create, sign, and submit. Okay, so here I have this new address. This would be my recipient address. Then I could import my personal information, my personal keys here. I have a private key, a public key of this particular address, right? So this is an already existing address in the ARC blockchain. I'll save this for later. I have to make sure that this address has enough balance to pay for the amount and the fee. So I can check that quickly using blockchain address data here. And I see that I have enough balance. Then I just have to decide on a fee and an amount that I want to use. I'll explain these quantities a little bit later in more detail, but for now, I just have to add all of this inside of the blockchain transaction function. So here I have this association with a blockchain base, I specify the blockchain base ARC here. I add the recipient, the fee, the amount, and I could also add this little message here with using this vendor field. Okay, so now what I have is a blockchain transaction object that has a summary of all of this information here. So next, the sender address has to sign this transaction using blockchain transaction sign. We include here the object we just created and the private key of that sender, right? So now this new object that appears is already signed and has these new properties, sender public key and the signature here. That's the important part. So these two steps, creating and signing, are both done locally. So we have not really sent this transaction to the blockchain yet. We do that with blockchain transaction submit. And if we did everything correctly, we should get this blockchain transaction object with the added field transaction ID. So this is our new transaction ID, but we still have to wait for this transaction to be picked up and added to a new block, and for that block to be forged by a delegate, in the case of ARC. So usually the amount of time we have to wait depends on the fee that we chose. But for now, let's review all of this information and some more details about ARC using the reading functions. So first, with blockchain data, I hope you can see it. I think it's a little bit small in the data set here. Sorry about that. But we can get some information like the latest block ID in the blockchain. We can get the total number of blocks and the fee statistics for each particular transaction type. So this is something about ARC. ARC has multiple transaction types. The one we just did is a transfer transaction type, which means that we are just exchanging currency between one address and a second address. They also have the second signature transaction that allows an address to basically add a second private key to their account so they can have increased security. They also have this delegate registration, so any address could register as a delegate for the ARC blockchain. And then this vote transaction that allows an address to vote for a particular delegate. So these are the ones we're supporting right now. And if you see this table here, we can use this as a reference for future transactions if we want to help us decide on a fee, right? So that's why I chose this one. And because these are quantities supported in the Wolfram language, we can easily convert those to have them as US dollars, for example. So that transaction cost me 1 cent. Yeah. And this one ARC Toshi is just the name of the minimum unit of currency in ARC. Yeah, and one ARC is the name of the main coin they use. So we're supporting all of it. Okay, so now we can review the newly created transaction. So the fact that we can even see this output here is because the transaction is already part of the blockchain. So everything worked out fine. Here we get a summary of the transaction, right? The sender, the recipient. This is the type, the transfer type. The amount, the fee, and here's our little message that we include. Something else that we can do here is check on the block ID. The block ID. So this is the block where this transaction is contained in the blockchain. So we can use blockchain block data now with that ID to look at our block, right? So here we had a lot of information about the block. For example, this generator field that I have here has information about the delegate who forged this block. So this is their username, their address, and their public key. And because they forge the block, they get that reward that I talked about, plus the fees of all of the transactions inside. But well, in this case, it's only my transaction. So here we can see that under the forged field. Here we can see the reward. This is like a static reward for forging one block, and this is the fee I used, right? So yes, the total of that. Now I can look at the address. That was the recipient address here, that's the new address, to see the information. And we see that the balance shown here is the amount that was transferred. So this is now the new balance that this address has, and they could use future transactions using this amount of money that they have. And here we also have the equivalence in US dollars and a list of all of the transactions, in this case only this one, right? Okay. Another thing we could do is compare the old and the new balance of the sender address. So that existing address that I have, here I save the old balance. I can get the new balance, doing the same thing once again, specifying here a subproperty of the output, and compare that new balance plus the amount plus the fees equals the old balance that I have. Yeah. So we could also look using blockchain address data, specifically at a delegate. This is the delegate that forged our block. And because this is a delegate, we get actually an extended output here with more information. Some important things, for example, the rank of this delegate is 39. So because he's inside of those top 51, he was able to forge this block. Here we can see the amount of votes they have, right? We could see using the voter for field, which delegate this address voted for. So in this case, obviously they voted for themselves, right? Yeah. And we could see a list of all the voters, all the addresses that use that vote type transaction to vote for this delegate. Yes, a lot of transactions, a lot of addresses here. And we could also see the information about this delegate's revenue using that forged field. So this is just a summary of that. So yes, this about sums up the ARC integration for Wolfram language.
Okay. Hi, my name is Akira Toma, and I am going to talk about our progress in Oracle. So what is an oracle? Initially, blockchains were developed to grab just simple cryptocurrency transactions into a decentralized ledger, and some of these transactions allow certain conditions in order to be valid, like the signature of different parties. And as the technology evolved, blockchains that support Turing-complete languages began to appear, letting developers to specify all kinds of conditions into the so-called smart contracts. But soon they realized that in order to create broader applications, they would need data from the external world. And since Wolfram Alpha is the largest computational engine in the world, used by various virtual assistants like Siri and Alexa, among others, it just seems natural to use Wolfram Alpha as the main provider of computational facts for smart contracts. So here's our proposed architecture for the Oracle. There are two main components in this architecture. The first one is the Wolfram Oracle contract that lives inside a blockchain, and the other one is the Wolfram compute nodes on the outside. A contract that wants to query alpha would internally call our Wolfram Oracle contracts that will trigger an event with all the query parameters, and then the compute node will listen to that event, take all the query parameters, make a request to alpha, and finally submit a transaction in order to deliver the data the user contract has requested. Currently, we are testing this architecture on the Ropsten testnet network of the Ethereum protocol. It uses natural language to interact with the Oracle, so there is no need for the developer to handle messy and poorly documented APIs. There are mainly two ways to interact with the Oracle. A developer might just copy and paste a piece of Solidity function code to their smart contract and use it, but it is also possible to deploy a contract and use it, interact with the contract using our various blockchain functions we have developed in the Wolfram language. So let's take a look at the Oracle. Here's the front end of our Oracle. We have an input box, and we have a couple of options. Right now, like I just said, we are supporting only Solidity for Ethereum, but we are doing some progress in integrating other blockchains soon. So let's make a simple query like, For example, if I want to, I'm using a Mac. I'm not used to using Macs. For example, if we want to know how much is an Ether in US dollars, let's look what the Oracle gives us. So it gives us a parsed Wolfram language expression and the result of the query. The developer, by looking the result, he can verify that this query is actually what he was looking for. Below we have a piece of Solidity function that he can just paste and copy and paste in his contract and interact with alpha. Now let's make a little bit more complicated query, like if we want to know the temperature in Boston. We can see here that the disambiguation is handled as well. So if the developer meant another city, for example, in Georgia, you just have to click it in the drop-down menu, and it will take us to the right query. And again, we have the parsed Wolfram language expression, the result, and the Solidity function.
Is this live?
Yeah.
Because the URL just says more.
Okay, yeah, that is because I made a mistake, but in any case,
the refresh button. The little circle thing, and then the URL will come back.
se romperá?
It's not public here. It's not
Yeah, it's not public.
It works only internally right now, so I prefer not to refresh the page. Yeah. Where was I? Now, if we change to the contract option, let's make a little bit another query. For example, we want to get a random integer between 10 and 50. And in this case, in the contract, we have again parsed Wolfram language expression, the result, but this time we have a whole contract of Solidity that we have that we can deploy and run. And I'm running out of time, so let's just get back to the notebook. So if you take the contract template, you could deploy it using our blockchain functions. And in order to deploy a transaction, you just have to make three things, which is create the transactions, including the Solidity code. You would sign it and finally submit it. It is as simple as that. And if you wait a few seconds in order to wait for the transaction to get mined, we can retrieve the contract address and we can verify that the state variable gets initialized with 0. I forgot to mention that the contract we just deployed, what it does is to store a state variable in the blockchain, and it gets updated with every call to alpha. Finally, if we want to call alpha, if we want to query alpha, we would create a second transactions following the three steps. We create a transaction with the query to alpha, we sign it, and finally we submit it. We wait for the Wolfram Oracle compute nodes to harvest the event, query alpha, and submit a final transaction. After a while, we can finally verify that here successfully we have written external data to the Ethereum blockchain. That sums up our progress with the Oracle. If there is any question about this or the ARC integration, we would be happy to answer you.